Good morning, students. Sage Anandam, continuing the lecture series of open analog and digital communication. Previous 4 lectures has been uploaded on the page. Let's continue with the lecture 5 on pulse modulation systems. So basically, what is pulse modulation system? In pulse modulation, the carrier is in the form of a train of periodic rectangular pulses. Pulse modulation can either be analog or digital. In analog pulse modulation, the amplitude, width or position of the carrier is changed in accordance with the modulating signal. This will result in pulse amplitude modulation, pulse width, or pulse position modulation. So basically, both the 3 modulation are the examples of the analog pulse modulation. The pulse modulation can be digital as well. And the classification of pulse modulation system is being described as follows. So analog pulse modulation will consist of pulse amplitude, pulse width, and pulse modulation. And digital modulation system will consist of pulse code modulation, delta modulation. We'll cover all these in this lecture series. So these are the waveforms of pulse amplitude, pulse width, and pulse position modulation. So this is the massive signal which we send, and we send a train of pulses like this for the carrier signal. In the pulse amplitude modulation, you can see the amplitude changes in accordance with the massive signal. In pulse width modulation, the width of the pulses changes. The point where we have the maximum amplitude of the massive signal will have contain the maximum width, and the point where we have the minimum amplitude of the massive signal will consist of the minimum width of the pulse. Similarly, with reference to the pulse width modulation, pulse position modulation is also there, where the position of the carrier pulses changes with respect to the pulse width modulation and in accordance with the massive signal. Now coming to the pulse amplitude modulation firstly. So before reading the pulse amplitude modulation, we need to know what is the sampling theorem. Okay. So in the pulse modulation and digital modulation systems, the signal to be transmitted must be in the discrete form. If the message is coming from a digital source, then it is in the proper form for processing by a digital communication system. But the massive signal can be either digital or analog in nature. So in the analog signal, the massive signal has to be first converted into a discrete time signal for the sampling. For this, converting an analog signal into a discrete form, we require a process which is known as the sampling. In analog signal case, it has to be first converted into a discrete time signal, and this is known as a sampling process. Thus, using the sampling process, we can convert a continuous time signal into a discrete time signal. So this provides a mechanism for representing a continuous time signal by a discrete time signal, taking sufficient number of samples of the signal so that the original signal is represented in its samples continuously. And the sampling should be done so that it contains all the information of the continuous analog signal. So for this, it can be stated into 2 points. First, a band limited signal of finite energy with no frequency component higher than the FM, where FM is the maximum frequency of the massive signal, is completely described by its sample values, which are at uniform intervals less than or equal to 1 upon twice of FM seconds parts. Then sampling frequency must be equal to or higher than twice of FM. That is, the sampling frequency Fs should be greater than or equal to twice of the maximum frequency of the continuous analog signal, which is described here. Fs is the sampling frequency and FM is the maximum frequency component of the message or the continuous analog signal. So this is how we can obtain the discrete time signal from a continuous time signal. Now, sampling can be of 3 types. First, impulse, then natural sampling, and third is the flat top sampling. Coming to the impulse sampling, which is also known as instantaneous sampling, impulse sampling, or ideal sampling. So, first coming to the impulse sampling. Impulse sampling can be obtained by multiplying the input signal xt with the impulse train of period ts. Also, it is known as ideal sampling or instantaneous sampling. Practically, it is not used because the width of the pulse cannot be zero and the generation of impulse is not possible. That's why practically it is not used. So there you can see from here that we cannot generate a pulse having the width equal to zero. It is next to impossible, and this is how the modulation can be obtained. But this is not used. So we use either natural sampling or flat top sampling. Coming to the natural sampling, what is it? The natural sampling is just similar to ideal sampling. The only difference in this is that instead of using a delta function having a width pulse width equal to zero, we use rectangular train of pulses that contains some of the width. Like this, it is shown here. This is your master signal. This is the carrier signal where a train of rectangular train pulses is used having some width. And this is how we obtain the discrete form of this signal. So natural sampling is also sometimes called as a chopper sampling. Now coming to the third portion. Third type of sampling is the flat top sampling. Here the tops of the samples are flat. That is, they have constant amplitude and is equal to the instantaneous value of the baseband signal at the start of the sampling. It makes use of the sample and hold circuit. How this circuit works, let me explain. Firstly, as the name suggests, it is flat top. You can see from here that it has tops flat. Earlier, we are not having flat tops. We are having the tops which follow the waveform of the massive signal. But here the tops are flat. It takes the instantaneous point of the massive signal, hold that signal, and then it leaves until it is discharges. Here, let me explain the sample and hold circuit. Input is given to two switches and a capacitor is joined in parallel with the discharging switch. So when the input is applied, this switch charges to its maximum value, like it charges till this point. Then this switch is open. Then it discharges through capacitor. This is the discharging point. That's why it is called hold. Then again, it starts charging. Then it drop down its voltage. So this is how it sample, hold, and then drops. It samples, holds, and then drops. This is how this waveform is being generated. Moreover, it has a drawback, like this portion is extra, which can create a noise, or this portion has been not taken in account. So this drawback of this circuit is known as the aperture effect. Now coming to pulse amplitude modulation. So basically what we have read till now, sampling, it is the pulse amplitude modulation only. How the amplitude of the pulse is varied. So amplitude of the pulse carrier varies in proportion to the instantaneous value of the amplitude of the massive signal. The width and the position of the pulses are constant in this modulation circuit. So this is the natural, this is the natural sampling or the pulse amplitude modulation, and this is flat top. Massive signal is sent, a train of pulse, the rectangular train pulse is sent as a carrier signal, and sampling takes place. This is flat top, and this is the natural sampling. And pulse amplitude modulated wave has been created. What are the advantages of pulse amplitude modulation? The generation and detection of this modulation is easy as sampling is going on, and the pulse amplitude modulation allows multiplexing. Basically, time division multiplexing is used here. Disadvantages: bandwidth required for transmission of pan signal is very large. Noise interference is very maximum in pan because of the aperture effect. Now coming to the pulse width modulation. So when the width of the, Yes. So when the width of the rectangular pulse is relatively higher, frequency carrier signal comprising of discrete pulses is varied in accordance with the amplitude of the analog modulating signal. It is known as the pulse width modulation. The amplitude of the pulse is constant while the width of the pulse is made proportional to the amplitude of the signal at the sampling instant. The pulse width modulation provides better noise immunity and allows use of amplitude limiters. It is also known as pulse duration modulation. In pulse width modulation, the information signal modulates the width of the pulse signal according to its instantaneous value while keeping the amplitude and position of the pulse constant. The larger the sample values, the wider the corresponding pulse, and vice versa. Pulse width modulation is a non-linear form of modulation as compared to pulse amplitude modulation, which is linear form of modulation. So basically, this is the waveform which I have explained you earlier, that if the information signal is slowly varying, that is sampled at a fast rate compared to the Nyquist rate, and then the adjacent pulses will have the same width. So the point where we have the maximum amplitude of the masses signal will have contain the maximum width of the pulse width modulated wave, and the pulse width modulated wave will have the minimum width where the amplitude is minimum of the masses signal. Coming to the last. Okay, we have the advantages and disadvantages of pulse width modulation also. So advantages are very good noise immunity, no need of synchronization between the transmitter and the receiver is needed. And the disadvantages are due to variable pulse width, the pulses may have variable power contents, and the bandwidth required for the pulse width modulation communication is large as compared to bandwidth of PAM. Now coming to the last, that is the pulse position modulation. So the pulse position modulation, when the position of a relatively higher frequency carrier signal comprising of discrete pulses is varied in accordance with the amplitude of the analog modulating signal, it is called as pulse position modulation. In pulse position modulation, the position of the pulses which is changed with respect to the reference pulse. The amplitude and the width of the pulse will remain always constant, unchanged, and does not carry any information. So the pulse position modulation will have better noise immunity and allows use of amplitude limiters. So this is the basically the waveform. This is the masses signal. This is the carrier signal. Pulse position modulation waveform is taken in with reference to the pulse width modulation. This is the maximum width, so the pulse will be near to it, and with having the minimum width have the position disturbed as compared to the reference to the carrier signal. So that's all. Coming to the last slide of the PPT, having advantages and disadvantages. So first, advantages of pulse position modulation. It has a good noise immunity. It is possible to reconstruct PPM signals from noise contaminated pulse position modulated signals. And the disadvantages, synchronization between the transmitter and the receiver is required as the position is varied. That's why we need synchronization, and large bandwidth is required to ensure transmission of undistorted pulses. This is the comparison between all the modulation techniques, analog pulse modulation techniques, which I have taught in this whole lecture is converted to a tabular form. So firstly, the variable parameter of pulse carrier here, which variable varies is the amplitude here with the position. Bandwidth requirement is minimum in PAM and higher in pulse width and pulse position. Transmitted power varies with amplitude of pulses. It varies with the width and it remains the constant. Noise immunity is lower in pulse amplitude modulation and higher in both. And the information here it is contained in amplitude, here in the width, and here in the position. And this is the waveform which we have earlier discussed. Thank you so much. If you have any queries related to this topic, please comment on the comment box, and please add this to your ADC playlist. And for further videos, stay connected. Thank you. Sejananda.